Right, so to video 2 of 5 in our unit on modular arithmetic. We're going to establish some rules in this video that we touched on in the first one, but we were looking more at specific examples. So let's start off with looking at some situations. So if A is equivalent to B in modulo M, and let's say C is equivalent to D in mod M. Okay, then what do we know? Well, we know that if this is the case, then we can say A plus C, or in fact A minus C as well. So A plus or minus C, will be the equivalent of B plus or minus D in mod M. So we can add and subtract our modular statements, our congruency statements. So let's just have a little look at how that works. In this situation here, what this says is that A is equal to M times some A plus B, and this says that C is equal to M times some B plus D. And if we then look at taking these two and adding them together, so A plus C will equal MA plus MB, so M lots of A plus B plus B plus D, and well, that's equal to, there's my remainder when divided by M, so it's MB plus D in mod M. So there's my proof for that. Now that's nice. Well, what else can we say? Well, we also looked at in the last YouTube at multiplying both sides. So if A is equivalent to B mod M, then won't Ka be equivalent to Kb in mod M? And the answer to that is yes. We know it. We can test it. We know that 20 in say mod 6 is equal to 2. Because there are 3 6's in 20 with 2 remainder, and if we double it to 40, well, in mod 6, that's 6 lots of 6 is 4, so yes, doubling and doubling works, and in fact that works for any k, and we can prove that by we're just going to take this statement here, which becomes this statement here, and we can perhaps just look at multiplying both sides here by k, so Ka will equal just k by Ma plus b, won't it? So and what that says in mod M is that it's Ka by M, or is it the other way around? M by Ka, M by Ka plus Kb. So what this is Kb in mod M. So Ka will equal Kb in mod M, and that's result 2. And this might be just losing track of our results here, but there's 2 of them. And we can also say that if we've got these equivalent statements here, we can combine them to say that AC will be the equivalent of BD in mod M. So that's our third and final, actually, because it doesn't work for division, and we'll come to division in a later episode. But can we prove this one here, that AC is congruent to BD? Well, we're going to go to do that. We would take these 2 statements here and link them. So AC will equal MA plus B by MB plus D. So from that we could say that AC is equal to MA plus B by MB plus D. All right, and that's going to be M by, all right, that's MAB. I'll just pause this for a sec. So I didn't want to bore you with all the steps, but this is quite a significant proof. So just multiplying both sides out, and then this right hand side expands to this. When take M out of the first 3 terms, and then we're left with BD. And what this means, therefore, is that AC is equal to BD in mod M. And that is what we were trying to find. So if we add another look at an example here, if we have, let's say, an example, or maybe it's best to go into example, just looking here, page 55. No, that's not. Okay, just an example to see where we are in so far. If 15 is 3 mod 4 and 10 is 2 mod 4, so let's just see how these things work. We've said that if we add 15 and 10, then therefore, so we're looking at this first one here, A plus or minus C is B plus or minus D. So therefore 15 plus 10 will equal 25. Which equals, I'm going to say that's 3 plus 2, 5 in mod 4, which is equal to 1 in mod 4. So we've got, so the 15 plus 10 being 25 is 1 in mod 4. We get the same by adding the 3 and 2 in mod 4, which is equal to 1. We could do that with 15 minus 10. So what we're saying here is that will be equal to 3 minus 2, or 1 in mod 4, which we know to be the case because 5 is 1 in mod 4. Let's have a look at one of these. If 15 is equal to 3 mod 4, multiplying both sides by 3, so we could say that therefore 45 is equal to 9 in mod 4, which is equal to 1 in mod 4, which is correct because we know that 45 is 11 fours plus 1, so that's multiplying both sides by something. Now if we look at AC equals BD, this third result here, then AC 15 times 10, so 15 times 10 should be the equivalent of 3 times 2, or 6 in mod 4, which is 2 in mod 4. Now 15 times 10 is 150, so checking that, 150 over 4, 148, 25, and that's 37 with a remainder of 2, which is what we've got there. So everything's mapping out nicely so far. The last one of these results we're just going to look at is that if where are we? If A is equal to B mod M and C is D mod M, then, actually, we're just going to look at one of these. So if A is, right, so lastly, all right, if A is equal to B in mod M, then we can take A to any integer power n, and that will be equal to B to the same power. That's just an extension of, it's not an extension of my multiplication rule. However, so it's got a life of its own. But if we've got, my page is not scrolling. Oh, there we are. So for example, if we've got, so say 4 being the equivalent of in mod, no, not mod 7, that's no use. In mod 3, 4 is the equivalent of 1 in mod 3, then 4 squared will be the equivalent of 1 squared in mod 3, and we've got that because that's 16 is 5 threes. In fact, we could say 4 to the power of 200 is going to be equal to 1 to the power of 200, and 1 to the power of anything is 1 in mod 3. So you can see the real power of establishing a remainder of 1 in that we can raise to very large powers. Another example that might help, in modular 6, a remainder of 3 is with a number, say, what's that? So 9. So 9 is equal to 3 mod 6. Then we can square both. 9 squared is 81, will be equal to 3 squared is 9 mod 6. So we'll just check that that's the case. 9 mod 6, which is equal to 3 mod 6. And 9 squared is 81, and we know that 81 goes in 13 times with the remainder of 3. So we could keep going, and we could say that 9 cubed. I'm not sure what the value of 9 cubed is, but I know it'll be equal to 3 cubed in mod 6. And 3 cubed is 27 in mod 6 is 3. So we're back to modulus of 3 there. Okay, looking at an example, find the remainder when 2 to the power of 30 is divided by 13. So let's use this now to find. Okay, let's look at this example. So what we want to do here, we want to find out when you divide by 13. So 2 to the power of 30 in modulo 13 is what we want to establish. 2 to the power of 13, and so we want to find this remainder. Let's have a look at this. So modulo 13, I know that 2. Let's look at some powers. I know that 2 squared is 4. I know that 2 cubed is 8, and 2 to the power of 4 is 16. What I want to do is try and establish a remainder that is small. So if we go through those powers of 2, we've got 2 cubed is 8, 2 to the power of 4 is 16, which is 3, which is quite small. But then if we keep going, 32 is a remainder of 6, and then 64, well, 64 is a remainder of minus 1. Now, so maybe we'll use 2 to the power of 6, which is equal to 64, right, which is equivalent to minus 1 in modulo 13. And now I can say, well, therefore, using this rule here, a to the n is equal to b to the power of n. If a is equivalent to b, then I can say that 2 to the power of 6 to the power of 5 will equal minus 1 to the power of 5 in mod 13. Now, therefore, that's 2 to the power of 30, and minus 1 to the power of 5 is minus 1 in mod 13. And minus 1 is the same as 12 in mod 13, just adding 13 on. So the remainder, therefore the remainder is 12. You can see here that the method was to find a power that gave me in mod 13 the smallest number possible, ideally 1. Let's have a look at another example. We're looking at exercise 5b now. We're looking in exercise 5b. Might just have a look at question 1 AI, and we'll look at BI as well. So if you pause at this point and have a go at those questions on page 55, and then come back and have a look. Okay, so part 1 of A is 5 to the power of 13, and we want that in mod 7, and we want to know what the remainder is going to look like there. So we're looking now for powers of 5 that give us in mod 7 a small number. So mod 5 in mod 7 is 5. 5 squared in mod 7 is 25, which is so 5 squared, if you start to write this down, 25 in mod 7 is 4, so that's not much good. 5 cubed is 125, which in mod 7, so 7's into 125. So this is the sort of thing you need to do. 7 sevens are 49, so that's a remainder of 6. So that's not much good. 5 to the power of 4 is equal to 625. Now 625 into 7. I don't know how this is going to go. 8 sevens are 56. 7's into 65. 9 sevens, that's a remainder of 2. So with 5 to the power of 4, you've got a remainder of 2. We might just be able to get away with that. So we could say 5 to the power of 4 is equal to, what did we say? 2 in mod 7. So it's not equals, is it? It's a now. 5 to the power of 4 is equal to 2 in mod 7. So therefore, if I cube that, I get 5 to the power of 12. I cube this, I get 8 in mod 7. And 8 in mod 7 is 1 in mod 7. And so therefore 5 to the power of 13 will be equal to, so what we're doing there is multiplying by 5. So that'll be 5 in mod 7. So let's just check that. So that's worked okay. Now if we go to B part 1, and if you haven't had a go at this, then do so. It's 6 to the power of 15 in mod 12. So in this, pause if you haven't had a go at this already, but we're looking now for powers of 6 that give us a low remainder on mod 12, ideally 1. So 6 gives us a power of 6 is 6 to the power of 1 is 6 in mod 12, no good. 6 to the power of 2 is 36, which in mod 12 is actually 0. So I can say that 6 squared, so now 6 squared is equal to 36, which is equal to 0 in mod 12. So that means that any multiple now of 6 squared is also going to be 0. So 6 to the power of 14 will equal 0 to the power of 7. So that's still 0 in mod 12. And in fact, if I now multiply both sides by 6, I still get 0 in mod 12. So we have 0 as our solution for B. Okay, now go and have a look at the rest of the questions in exercise 5B, and I'll see you for part 3 of our series and 5C when you're ready for it.